According to the National Electrical Code, the size of the equipment grounding conductor, or EG, cannot be larger than the phase line size. The NEC provides tables, specifically Table 250.122, to determine the minimum size of equipment grounding conductors for grounding raceway end equipment. These tables correlate the size of the overcurrent protective device, such as a circuit breaker or fuse, protecting the circuit, to the required minimum size of the EGC. The overcurrent protective device is selected based on the ampacity of the phase conductors, which in turn are sized to carry the intended load. The EGC is sized to safely conduct fault current back to the source, allowing the overcurrent protective device to trip and clear the fault. The NEC specifies the minimum size of the EGC to ensure it has sufficient ampacity to handle the prospective fault current. The NEC doesn't require the EGC to be larger than the phase conductors because its primary function is to carry fault current for a short duration, not continuous load current. The phase conductors, on the other hand, are sized to carry the continuous load current. An oversized EGC wouldn't necessarily improve the safety or performance of the grounding system and would only add unnecessary cost. The selection of the proper EGC size is crucial for personnel safety and equipment protection. In the event of a ground fault, the EGC provides a low impedance path for fault current to flow back to the source. This low impedance path allows the fault current to rise quickly, causing the overcurrent protective device to trip and energize the circuit, minimizing the risk of electric shock or fire. Firstly, understanding the relationship between the overcurrent protective device, phase conductors, and EGC is paramount for proper electrical system design and installation. Secondly, always refer to the latest edition of the NEC and consult with a qualified electrical professional for specific application requirements. Thirdly, the NEC provides detailed guidelines for sizing and installing EGC to ensure electrical safety. The general principle is that the EGC must be sized appropriately to safely carry fault current, but it does not need to be larger than the phase conductors. This approach balances safety, cost, and practicality in electrical system design. Now let's delve deeper into the rationale behind this principle. The equipment grounding conductor's primary function is to provide a low impedance path for fault current to return to the source in the event of a ground fault. This low impedance path ensures that the fault current is high enough to quickly trip the overcurrent protective device, such as a circuit breaker or fuse, thereby minimizing the duration of the fault and reducing the risk of electrical shock or fire. The size of the EGC is determined by the size of the overcurrent protective device protecting the circuit, as specified in NEC Table 250.122. The table correlates the ampere rating of the overcurrent protective device to the minimum required size of the EGC. The overcurrent protective device is selected based on the ampacity of the phase conductors, which are sized to carry the continuous load current. Since the EGC is intended to carry fault current only for a short duration, it does not need to be sized as large as the phase conductors, which are designed to carry continuous load current. Furthermore, an oversized EGC would not necessarily improve the performance of the grounding system. The impedance of the grounding path is determined not only by the size of the conductor, but also by its length and the quality of the connections. Therefore, simply increasing the size of the EGC without addressing other factors that contribute to impedance may not significantly reduce the fault clearing time. In some cases, using an EGC that is too large can actually create problems. For example, if the EGC is significantly larger than the phase conductors, it may be more difficult to make proper terminations, which can compromise the integrity of the grounding system. Additionally, a larger EGC may require larger and more expensive fittings and connectors. The NEC provides specific requirements for the materials and installation of EGC to ensure that they provide a reliable low impedance path for fault current. These requirements cover factors such as conductor material, size, and type, as well as the methods for making connections and terminations. It is important to follow these requirements carefully to ensure that the grounding system is effective and safe. The NEC also addresses the use of different types of EGC, such as wire type, cable type, and metal raceways. Each type of EGC has its own advantages and disadvantages, and the selection of the appropriate type depends on the specific application and installation conditions. Wire-type EGC are commonly used in branch circuits and feeders, while cable-type EGC are often used in flexible cords and cables. Metal raceways such as conduit and cable trays can also be used as EGC, provided that they meet certain requirements. When using metal raceways as EGC, it is important to ensure that all connections are properly made and that the raceway is continuous and electrically conductive. This can be achieved by using listed fittings and connectors and by following the manufacturer's instructions. The NEC also includes requirements for the identification of EGC. EGC must be identified by a continuous green color or by a bare conductor. This requirement helps to ensure that EGC are easily recognizable and are not mistaken for other conductors. In addition to the general requirements for EGC, the NEC also includes specific requirements for grounding different types of equipment and systems. For example, the NEC includes requirements for grounding equipment enclosures, motor frames, and transformers. These requirements are designed to protect personnel and equipment from electrical shock and fire hazards. It is important to consult the NEC for the specific grounding requirements for each type of equipment and system. In summary, the NEC does not require the EGC to be larger than the phase conductors because its primary function is to carry fault current for a short duration, not continuous load current. The size of the EGC is determined by the size of the overcurrent protective device protecting the circuit, as specified in NEC Table 250.122. It is important to follow the NEC requirements for sizing and installing EGC to ensure that the grounding system is effective and safe. The NEC approach balances safety, cost, and practicality in electrical system design. It's also crucial to understand the difference between equipment grounding conductors and bonding conductors. While both are essential for electrical safety, they serve distinct purposes. The equipment grounding conductor, as we've discussed, provides a path for fault current to return to the source, tripping the overcurrent protective device. Bonding conductors, on the other hand, connect non-current carrying metal parts of the electrical system together to create an electrically conductive path. This path ensures that all metal parts are at the same potential, minimizing the risk of electric shock. The size of bonding conductors is also specified in the NEC, and it's important to select the appropriate size for the application. The NEC also addresses the grounding of separately derived systems such as generators and transformers. A separately derived system is an electrical system that is not directly connected to the utility power grid. The grounding requirements for separately derived systems are different from the grounding requirements for systems that are directly connected to the utility grid. It is important to consult the NEC for the specific grounding requirements for separately derived systems. Proper grounding is essential for electrical safety and equipment protection. By following the NEC requirements for sizing and installing EGC and bonding conductors, you can help to ensure that your electrical system is safe and reliable. Always consult with a qualified electrical professional for specific application requirements and to ensure compliance with all applicable codes and standards. They can assess the specific needs of your installation and provide expert guidance on selecting and installing the appropriate grounding system components. The continuous safe operation and function of electrical systems depend on effective grounding practices. The proper selection and installation of equipment grounding conductors, in accordance with the NEC, is a cornerstone of these practices, contributing significantly to the prevention of electrical hazards.